This is Leonard Evans telling you about a study by Jay Wiseman and me about safety benefits of a traffic signal designed for the color deficient. Traffic signals are ubiquitous, despite which there is not a reliable estimate of how many traffic lights there are in the United States. We do, however, have estimates of the annual number of crashes at signalized intersections. The data are from a 2010 NHTSA study, shows 2,635 fatal crashes occur at color vision deficiency. It's the decreased ability to see color. It comes in various forms, but the most common form is the inability to clearly distinguish red from green. About 7% of US males have this problem, compared to just 0.4% for females. These numbers imply that over 8 million drivers who cannot clearly distinguish red from green are traveling around in a nation with at least 1 million red-green traffic signals. This looks like a potential problem. It's a problem that Jay Wiseman has addressed with this novel traffic signal. In 2012, after 10 years of effort, Jay got a patent for this novel traffic signal aimed particularly at the red-green color deficient. Lab tests showed that the color deficient responded to the top rectangular shape 136 milliseconds faster than to the regular light. Armed with this, Jay was seeking to relate it to safety. After various inquiries, he got in touch with me. My approach to the problem builds upon material starting on page 182 of my book, Traffic Safety. Consider a red-green color-deficient driver traveling over the crest of a crest vertical curve and being suddenly confronted by a red light of a novel traffic signal. His speed is v1, total reaction time t1. He manages to come to a safe stop just in front of the stop line by applying maximum braking, which produces a constant deceleration A. The total distance of travel, d1, is given by this simple formula. The crest vertical curve has no effect on the calculation. It is there purely for expository convenience. Now consider case 2, the same scenario as before, but with a traditional traffic signal. The driver can still arrive safely at the stop line, even with the slower reaction time, provided his speed, now v2, is lower than his former speed. The distance down the roadway, d2, is given by the equation here, same as before, with 2's substituting for 1's. Because it's the same scenario, we have that d2 is equal to d1, and this enables us to solve for v2 in terms of the various quantities introduced. What we found is that the color deficient driver can keep risk unchanged by reducing speed slightly. It is convenient to express this speed reduction as a percent, which is given by the equation in terms of the quantities we've introduced. With the novel signal, the driver has a level of safety as if he were traveling PV slower. He's actually traveling at the speed he is traveling, but his risk when confronted by this novel signal is as if he were traveling slower than he is. This should be clear with a specific example. We have delta equal to 136 milliseconds. We take t1 equal to 2.5 seconds. It takes drivers a lot longer to respond to something unexpected in traffic in laboratory experiments. We take a equal to half the acceleration due to gravity and v1 equal to 50 miles per hour. Plugging these quantities in gives PV equal to 1.9%. This value is relatively unaffected by different choices of any of the other quantities, with the exception of delta. And of course PV is approximately proportional to delta. There are formulae in my book, Traffic Safety, that relate the percent change in risk to the percent change in speed, where n is an integer that has the value 2 for any crash, 3 for a serious injury crash, and 4 for a fatal crash. A reduced reaction time of 136 milliseconds, improved safety as if you were traveling 1.9% slower. Recall the number of crashes at signalized intersections, the number of color deficient drivers we're going to take as the average of the males and females. This underestimates things for the higher crash severities, but we do need to keep things simple. We estimate that there are 97 fatal crashes involving color deficient drivers. The improved signal makes the indicated reduction in those number of incidents so that the improved traffic signal will prevent 7.4 fatal crashes per year. The above is all for color deficient drivers, but additional geometric cues help everybody, but with a lower value of delta equal to 106 milliseconds. When we plug that into the data for all crashes, we find that this novel signal would prevent 156 fatal crashes in the nation per year. We've estimated the safety benefits for the color deficient population. These additional geometric cues benefit all road users, and that's pretty much like what we find in changes designed to help older drivers. They help everybody. For more information about the signal, please contact Jay Wiseman at photowise@hotmail.com.